Hi, and welcome to the 13th video in Aerodynamics. Last time, we finalized our theoretical exploration of aerodynamics with thin airfoil theory. With this theory, we could use superposition of vortex elements along the chord to analytically solve for the performance of thin wings with camber. It was the culmination of many previous topics and is a powerful tool we still use today. In this lecture, we're going to take a slight break from the mathematics and review things a bit more physically. We are starting with moving into the realm of realistic aerodynamic analysis, meaning accounting for viscous drag and three-dimensionality. Before we do that, I wanted to formally introduce the airfoil, or the cross-sectional shape of a lifting surface, and the wing, which is just the airfoil brought into the third dimension. So with that, let's jump right in. Today, we're going to talk about the lifting surface, and specifically the physical features, history, and modernization. Although it is most common to associate foils and wings with aircraft, it's important to realize that these principles also apply to turbofans, propellers, turbines, road vehicles, and even birds and fish. Let's start with a brief history of airfoil shape, specifically what led us to understand the importance of camber and thickness. In 1804, we saw the first modern aircraft configuration, and it was born with the design of glider by George Cayley in England. It was a hand-launched glider that was more like a kite than a modern aircraft. Later in the 1800s, we have the first wind tunnel experiments used to design airfoil shapes. These were carried out by Horatio Phillips. Notice that, although there was some essence of camber in these patented designs, the foils were tremendously thin. Wind tunnel measurements like these influenced the design of the Wright brothers, which was famously the first to flight. But the tradition of thin, terribly performing airfoils was continued. World War I was very influential to aircraft development and acted as a catalyst for engineering design. Three of the most common airfoils you would have found early in World War I were the Eiffel 14, the RAF-14, and the Albatross, from France, Britain, and Germany respectively. All were incredibly thin airfoils. And then, Prandtl came along and designed the Göttingen 298, a thick airfoil with absolutely superior performance. Once it found an aircraft in World War I, its capability for high lift meant better takeoff and landing characteristics as well as maneuvering in flight. It was so dominant that turning over the aircraft with the Göttingen foil was explicitly part of the armistice that ended the war. Shortly after, it became clear the importance of combining thickness and camber on foils. In the 1930s, NACA set out to standardize the first designs that gave the user the capability to modify the shape. These profile shapes were predominantly driven by guesswork and experiments. Then, panel methods and computers came about, and we were able to optimize foil shapes from our desk. A computer can more easily change the foil shape than it is to change an experimental model. Computer-optimized designs, like the GW1, later named the NASA LS, were capable of 30% more lift and 50% better efficiency than the leading NACA foils at the time. To this day, computers are the ultimate design tools for a foil shape. So, what exactly went so wrong in our thought process that led us down the path of thin foils for decades? There were a couple of reasons. First, being tradition. Cayley did it, and eventually people iterated on what Cayley did. Also, biomimicry took a lead role in this. These types of foils are common for birds, so we thought it must be best for flying. And what I think is most important is that bird flight and early experiments were limited to small models and low speeds, meaning low Reynolds number. At lower Reynolds numbers, viscous drag becomes more important relative to everything else, so thickness leads to high drag, which explains why birds have such thin foils. They have lower Reynolds numbers. However, at higher Reynolds numbers, this drag proportion goes down, so thicker foils are not as penalizing from a drag standpoint, and the thicker foils can reach higher angles of attack without separation. Now that we know better, we can approach modern airfoil basics. Here, let's draw a big airfoil. The foremost tip of the airfoil is the leading edge, and the back end is the trailing edge. The chord line is the line that connects the leading edge and the trailing edge. Notice the chord line can leave the foil if it's bent enough. The foil is made up of an upper surface curve and a lower surface. The camber line, by definition, splits the distance between the upper surface and the lower surface. It defines the bend of the airfoil. The thickness of the foil is the distance between the upper and lower surface. And the camber is defined by the camber height, the distance from the chord line to the camber line. Lastly, there can be an incoming flow with an angle of attack relative to the chord line. Typically, when you need an airfoil, you first choose your foil family. These help describe shape aspects of the foil for you. For example, the NACA series is wildly popular. Then, you might be able to choose your thickness parameters. Here it's mostly the max thickness, but also possibly the location of the maximum thickness. And lastly, you choose the maximum camber height and the location of that max camber. Some foils don't give you this level of control, and some do. Very loosely speaking, our end goal for a lifting surface is to turn the air as it passes over the object without disturbing it. The turning, as we've learned from circulation in elementary flows, is what gives us the lift. However, if we're too dramatic and cause separation or rough flow, that leads to high drag. Ideally, we want high lift and low drag. Let's compare flow over a flat plate to an airfoil at the same angle of attack. The sharpness of the plate will cause flow to separate very early, leading to an unsteady mess downstream. However, the airfoil delicately guides the flow downwards, mostly due to this thickness and camber we've been talking about. It's fair to ask, what makes a shape aerodynamic? The rules that I suggest are as follows. You want smooth surfaces. This means avoid bumps or divots that disturb the air. Also, roughness should generally be avoided, though technically sometimes promoting turbulence is a good thing, that we'll talk more about later in the lectures. Both of these things lead to lower skin friction drag. Second, you want to be slender. Avoid changing shape too fast with respect to the flow. Otherwise, it will separate and your performance will plummet. Specifically, you want to avoid closing your shape too fast. It is the flow expansion at the back end that leads to separation. Generally speaking, for low-speed airfoils you want round leading edges. This helps flow bend around and guide downwards. Sharp leading edges lead to early separation. And on the trailing edge you want the exact opposite, sharpness. This does a few things that are beneficial. First, it enforces the cutter condition, which means the stagnation point stays at a known fixed location on the trailing edge. No flow is allowed to bend around this sharp edge. Second, it lets the streamlines meet gracefully in parallel with as little disturbance as possible. Colliding streamlines from the top and bottom surface can lead to messy flow with energy loss in the wake. Let's compare the typical lift performance of a NACA foil to a flat plate. The dashed line is the lift curve for a flat plate. It increases linearly, but at some point reaches massive separation and the lift maxes out. The airfoil, however, has an offset due to the added camber. The lift slope is the same, as we learned with thin airfoil theory, but improved by a delta CL. We've also increased our maximum lift by a large amount, roughly double what a flat plate is capable of. Just by adding thickness and camber, we can now lift double the weight for the same airflow. But that's just the fixed shape. What if we need to modify the performance? Say we want to change forces or moments during flight. Throughout a typical flight, the aircraft goes through different stages and needs change. For example, in takeoff, cruise, and landing, the needs are all very different. If the aircraft has to adapt to wind or turbulence, it needs to adjust. Or maybe a maneuver is required to get around something. All this means that an airfoil needs to do two main things. They need to have the capability to actively change their lift, drag, or moment, and they sometimes need as high a lift as possible. Let's explore why. Consider an aircraft that's landing. Ideally, we want to land as slow as possible. It's safer, easier to control, and landing with less energy means braking is easier and faster, and there's no need for beefy landing gear that weighs a ton. Consider the lift equation and let's explore how to reduce our speed. Here, the lift needed is relatively constant at our vehicle weight. Most of the terms on the right-hand side are also constant, so not much to do there. What we find are the two knobs we can turn our velocity and lift coefficient. So, if we want to minimize the velocity, the only thing we can do is maximize our lift. Many modern airfoil designs come with considerations for altering the lift. We can do things to enhance lift at both the trailing edge and the leading edge of the foil. Let's look at what we can do with a simple trailing edge flap. Compare a symmetric foil with and without a flap. With the flap deflected, the flow is turned downwards, so the streamlines indicate lift. On the CL versus alpha graph, we can plot the lift. The solid line is the base case without deflection, and the dashed lines represent the lift curve at plus and minus 10 degrees flap angle. Note here that the flap simply acts as an offset to the lift curve. With the flap engaged, we can significantly alter the maximum lift coefficient of the foil. These types of flaps are not only used in landing, but also used as active control surfaces all over the aircraft. At the leading edge, there are other options. We're going to highlight leading edge slats, but droops and flaps are also common. A slat is a part of the nose of the foil that extends outward, causing a gap between the nose part and the foil. Compare the streamlines of a foil at a high angle of attack with and without the slats. Where flow separates on the foil without the slat, it stays attached with the slat activated. This is because the slat allows flow through the foil and acts as a pressure relief where the flow is most likely to separate. Drawing the lift curve for this situation, the solid line represents the foil without the slat activated, and the dashed line represents with the slat. What we notice is that the slat significantly improves our angle of attack range before separation and also leads to much higher lift coefficient. Both of these technologies are utilized in modern airfoil designs, but to super engineered level. Take the typical configuration of a foil in cruise. The foil takes the standard shape we're accustomed to, but you'll notice it is constructed from multiple parts, with the blue parts being actuatable. In cruise, we need high speed, relatively low lift coefficients, and low drag. So, we stay at lower angles of attack and we get the foil shape as low drag as possible. But in takeoff and landing, it's a different story. All of a sudden, like a transformer, these blue pieces come out of their housing. The leading edge slat extends to allow the foil to go to higher angles of attack. The flaps extend out and create an elongated camberline with multiple pieces. This is because when we land, we need low speed, high lift, and we don't care as much about the drag. As you can see, the design of the simple airfoil has really changed over the past century. Now we can consider the third dimension, when airfoils turn into wings. If you squint at almost any commercial aircraft, you'll notice one main consistency. They're basically tubes with wings extending out in a ton of different places. The wings make the control force, and the tube carries the stuff. Interestingly, this is where aerodynamics meets other engineering disciplines. Wings are more than just aerodynamics. They need to worry about aircraft structure and strength of material. Weight needs to be considered, and then stability and control. Note, this is a very rough outline of wings and their configuration. For more information, the wiki article on wing configuration is tremendous. Let's go over the basics of the main wing configuration. Let's say you want to put a wing on an aircraft. There are a lot of things to consider. First is how many wings you want to have. There are monoplanes with a single wing, biplanes with two stacked wings, triplanes, quadplanes, multiplanes, etc. You would do this if you wanted to get more lift out of a single fuselage space. However, this is kind of an old parameter and not really considered in modern aircraft. We get the lift we need from single foils. Second, you want to choose where on the fuselage the wings are positioned vertically. This alters the aircraft's stability, and all different types are common even today, either on the belly of the fuselage, in the middle, or on the shoulder. Next, you want to figure out how to support your wings. If they're strong enough, you can just cantilever them out to the side. However, if they're thinner or with weaker material, they might need to be braced. These structural considerations are mostly aged out with our advances in structure design and material strength. Fourth, we want to consider our wing aspect ratio, which is super important. This is the span versus the chord. High aspect ratio rings are very efficient, which we learn about later in the course, but come at the penalty of needing higher strength and weight due to the larger moment caused by the lift near the wingtips. Next, you can choose to either have the chord length be constant along the span with a rectangular wing, or you can vary it. Tapered and elliptical shaped wings are typical, and delta wings are common in more aggressive aircraft. Altering this parameter impacts your induced drag and efficiency, though it comes at a penalty in controllability and separation characteristics of the foil. The wing sweep, which is how the wings are angled from top-down perspective, is also common to vary in modern aircraft. This helps in case you have to mount your wing root at a non-ideal location on the fuselage and want to alter your true position of the lift. Also, the sweep impacts flight stability. And lastly, we can adjust the hedral of the wing, which is a word I just made up. A dihedral wing has the wings angled upwards from a front perspective, and an anhedral wing are angled downwards. Like the sweep, this angle impacts flight stability and control. Now that we know the basics, we can also consider more modern modifications to wings. We will explore ways wings modify performance and control of the aircraft. Draw a main wing cantilevered from a fuselage, flying towards the top of the page. There are primary control surfaces all over the wing. In the back, we have flaps and ailerons that alter the wing lift and induce roll. In the leading edge, we can have flaps or slats in various places for when we need to go to very high angles of attack, as we saw with modern airfoil design. Secondary to these are the flow control devices over the surface. Some are designed to control any flow that moves in the spanwise direction or sideways in this view. It generally is unwanted and hurts performance. Fences, notches, and teeth are all used to mitigate spanwise flow. At the end of the wing, we very commonly see wing tips. These prevent flow from rolling from the bottom to the top surface of the foil and minimize the tip vortex. Also, we might want to try some flow control in the streamwise direction. Most commonly, these are vortex generators. Little tabs that produce a vortex keeping a boundary layer energized and flow attached to the foil. Underneath, we might have vortilons, which use the local spanwise flow to generate vortex structure, turning a flaw into a feature. Near the root, we can have leading edge root extensions. When an aircraft is at a high angle of attack, flow near the root is susceptible to separating first. So, with these extensions, at high angles of attack, a vortex is generated limiting separation. Downstream, we also have secondary wings in the tail or empennage. These house primary control surfaces too. The elevator controls the pitch angle, and the rudder controls the yaw. These also commonly have smaller trims, which you set and forget to get a constant effect that the pilot doesn't need to worry about adjusting all the time. To summarize, these are the basics of 2D airfoils, where we primarily care about aerodynamics. And how they turn into wings, where aerodynamics, structure strength, weight, stability, and control all need to be considered simultaneously. Let's review what we've learned today. We started with a brief history lesson of how airfoils got their shape, specifically the importance of camber and thickness. We learned the basic features of an airfoil, and what makes these airfoils aerodynamic. Modern foils use combinations of leading edge and trailing edge devices to achieve maximum performance and control. After this, we moved to wings and considered all of the decisions you have to make when you put a wing on an aircraft. Lastly, we went over the basic anatomy of modern wings and their control surfaces. And that is the physical introduction to both airfoil and wing design. I hope you enjoyed the video, and thanks for watching.